Okay, so we're starting a unit on energy, and you might be wondering why we're doing a note on something called work. So first thing I want to start off by saying and showing you is that work can be defined. So we think of work as maybe having a job or doing some sort of exercise is work for us because we feel tired after. But when we talk about work in the scientific form, it's really, by definition, the amount of energy that's transferred to an object by applying a force to something over a certain distance. So in a sense, it can apply to those two situations that we think of in everyday life work, but in scientific terms, work and energy are related. So in order to do work, we're applying a force to some object and we're moving it. And when we're doing that, we're expending, I guess, some type of energy. And so work and energy are completely related. We need energy to do work, and work is transferring a form of energy, depending on what type of work we're doing. So if we want to look at how we can mathematically calculate the amount of work done on something, there's a formula that we've got. So our formula for work. So work is a capital W, and it's equal to the amount of force. So you've seen this symbol before, and this means multiplication. When we put a little dot here, that means multiplied by how far we moved an object. So we're applying a force to an object, we're moving at a certain distance, and in order to calculate the amount of work, we're just taking the force times the distance. Now, if you remember, let's look at this first. Force, so F is force in newtons, so we've done this already. And we've also seen this triangle means change in, so the change in displacement, I'm just going to make this a little bit thinner, is displacement. And displacement, if you recall, is measured in meters. So this is a capital N, this is a lowercase m, and what we're finding here is work. And work is measured, let's not do that. Let's just simply say work in. Think about what we're doing. We're taking a newton and we're multiplying it by a meter. So really what we're calculating is called a newton, and we put a little dot here, meter, a newton meter. Now, a lot of times in physics we come up with units for our final answers, and there's also another way of stating these, and it's usually because it's measured off, it's usually named after some scientists. So a newton meter is also known as, so let's say AKA, also known as a joule. So either or is correct in your final answers, and that's a capital J. So work can be measured in newton meters because we're taking a force and multiplying it by displacement, or also it could be measured in joules. So either or is acceptable. Now, and one important thing here to note, that the force that you apply to an object and the displacement, so where it moves, have to be in the same direction. So if we push, we attempt to push a desk to the right, so we're applying a force to the right, in the right direction, that desk has to move in that direction in order for it to be called work. Okay, work has to be done if the displacement and the force vectors are in the exact same direction. So let's look at an example. A store employee exerts a horizontal force of magnitude 44 newtons, so here's our force, on a set of carts. How much work is done by the employee when pulling the carts 15 meters? So here's our displacement. So we've been given force is equal to 44 newtons, and our displacement is equal to 15 meters, and what we're trying to find is work. Okay, so basically this is just a direct substitution, and we end up with 44 times 15, and we end up with 660. You can either have newton meters, I will accept either, or joules. So newton meters or joules. So the amount of work done on this cart, based on the amount of force that was applied, is 660 newton meters or joules. Okay, so here's an example of when the force and the displacement are in the exact same direction. What happens when they're not in the same direction? Okay, we get something called negative work. If force is, and I think there's, something here. If force is in the opposite direction of the displacement, so let's just think of example, friction is an example of a force that works in the opposite direction of what we're trying to move. All that happens is that the work done becomes negative. Okay, so what we end up with, example 2, consider the situation in example 1 and except this time a second employee exerts a horizontal force of 14 newtons on the carts but in the opposite direction. So there's more work being done and it's in the opposite direction. So we should find out how much work is being done by this situation, the second employee. So this employee is exerting a force still of 14 newtons. And the cart is still moving 15 meters. So we can calculate the work. So work by the second employee is 14 times 15, and we end up with 210 joules. And now we just want to know what the total work done is. So if we think of work total is equal to work 1, which is in a positive direction, let's say, plus the sum of any other work, and this one's in the opposite direction, so it's working against it, it's going to be a negative. So the total work is the sum of all of the work done, but we're looking at this second one is in the opposite direction, so we're actually end up subtracting it. And so what we end up with, our answer was 660, so we end up with the 660 by the first employee minus the 210 from the second employee, and the total work done on this cart ends up being 450 joules. Okay, and that has to come up again. Okay. Now, that happens if we're moving things horizontally along the ground or we're sliding things horizontally. What happens if we're lifting an object above the Earth's surface? So remember back from our forces units that when we're measuring the weight of something, it's really also the same as the force of gravity. And so when something feels heavy, it's because it has a lot of mass and gravity's pulling it down. And so in order to calculate what that force of gravity is on the object, we always took the mass in kilograms times gravity, which was 9.8. And so if we think that we're going to lift objects off the ground and basically we're doing work against gravity, there's a different way of calculating that. And I'll show you. So let's reveal here. To lift an object, an upward force must be applied against the downward force of gravity. The force in this case is equal to the weight of the object, also known as the force of gravity. So just as a recap, this is basically what I just said. Remember, the weight of the object is equal to the force of gravity, which is also equal to its mass times 9.8. That gravitational constant never changes. Okay, so the weight of any object is mass times 9.8. So a bag of groceries with this mass, 8.1 kilograms, is raised vertically at a slow, constant velocity from the floor to a countertop over this distance. Calculate the force needed to raise the bag at a constant velocity and calculate the work done on the bag of groceries by the upward force. So let's look at A first of all. What force would be needed to lift 8.1 kilograms? Well, the reason it feels heavy is because of gravity, and that's an object's weight. So if we think of an object's weight being equal to the force of gravity, it's mass times gravity, which is equal to mass times 9.8. And the mass of this is 8.1 kilograms times 9.8, and we end up with 79.38 newtons. So this answers A. What force would we need to overcome gravity and lift this object up? Well, if the weight of it is 79 newtons or 79.38 newtons, then in order to lift that, we need a force equal to that or greater. So that answers A. Now, how about the work done? So for part B, work is equal to force times distance. The only difference here is, and this will apply to every situation that we're lifting something vertically, is that if we're trying to lift something against gravity, this force becomes the force of gravity, because that's what we're working against with our force. And our distance we're moving it is still a distance in meters, but because we're lifting it vertically, all it is it's a vertical distance. So instead of saying d, we call it height. So a change in height, and it's still both measured in meters. So if we think about this, the work in lifting any object up is the force of gravity, which we just calculated here. So it's always your mass times 9.8. So we end up with 79.38, and multiplied by the height that it was lifted. The height is 92 centimeters. Be on the lookout for this though. We don't want our units in centimeters. Remember that 1 meter is 100 centimeters. So if we were to divide this by 100, we end up with, so divided by 100, just so you know where that came from, we end up with 0.92 meters is the distance we lifted it. And so now we have our force times our distance. And the only thing that changed is that we're moving things vertically. So if we're moving something vertically, we're working against gravity, so that's the force that we need. And if we're moving something vertically, we just don't call it distance, we call it height, because we're now moving it above the Earth's surface. And so we end up with a total force of total work done of 73 joules. Okay, and the one last thing I wanted to go through, I don't think I have anything else in this note, no, but you're going to be asked to solve questions, so be on the lookout for this. Vertical movements mean that this equation becomes this. If we're moving something above the Earth's surface or against gravity, it becomes the force, becomes gravitational force, and the distance just becomes your vertical height. Okay, and this, so you always know, is your mass in kilograms times 9.8, always. Okay, and the one final thing I want to go through is, because we have a new formula, so this general formula equals force times distance, we can give you a triangle for that, so that you always have, and I think this will be on your formula sheet so you don't really have to worry, but just recall that if we have a magic triangle, we have force down here, distance, and we have work. So remember, cover up the one you're looking for. So let's just say you were given the amount of work done and the distance, and you had to work backwards and find out what force was required to get that amount of work done in that distance. So if we wanted to solve for F, we cover up this F and we see what's left, and it would be work divided by distance. If we were solving for distance, we would cover this one up and say that we're solving for distance by taking work divided by force. So this is your magic triangle for force, work, and distance. Okay?